today we are looking at the topic called cross-validation, and we are basically doing its practical implementation. So basically we are on a platform called Kaggle. Okay. So this is a platform dedicated for running machine learning algorithms. It supports Python and R. So this is a very good platform. So you can just dive and see which all cross-validation techniques we are going to practically implement. So for the training and testing purpose and validation purpose, I'll be using something called iris dataset, and this dataset is available on sklearn. And apart from that, whatever libraries I'll be importing, that will be imported from sklearn itself. So basically in the theory we looked at some of the cross validations such as Holdout, KFold, Stratified KFold, leave out, and one more time series. So we'll be looking at all of these in this practical implementation. So let's try and run what we can do with this. So let me run the first cell. So you can just shift enter into this cell to run this cell. So you can just click the play button. It has run. Now first we are looking at holdout cross validation. So let me just give you some brief intro about holdout cross validation. So let's say this is our data set. Okay, and from this we'll be divided into some part to validation or test and another for training. Let's say this is 70% and this is 30%. Okay, here also we will be having something called random state, and that will be deciding the split of this content. So based on this random state, what will be getting different accuracies. Okay, so this is how it's gonna work. So let me walk you through the code. Firstly, we'll having load iris dataset. We are having train test split. Obviously, we are having logistic regression, and we are having accuracy score. Firstly, we are loading the data. Target and data is being loaded into X and Y variable. We'll be printing that size of the data. We will be building a logistic regression model, and this is where we are doing holdout cross validation. This is the train test function. We are giving X and Y, and this is test type, means 70% will be training and 30% will be testing. And this is the random state I was talking about, random state. And this is where we are printing the model accuracy on the training and test. So let's try and run this. So we run. Okay, so the training accuracy is 96% approximately, and it's a surprise that it's giving 100% accuracy on test data. So it doesn't generally happens, but here you can see it's 100%. I don't know how, but okay. And there was around 150 samples, so they are not much in number, so probably the data gets some overfitting condition. So that's why it's giving 100%. Next is KFold cross validation. So what we basically do in KFold cross validation is we have this data and we decide a K, and let me draw some of the examples for K. And let's say we have K equals to 4. So for first iteration, let's say this becomes our validation data and remaining on training. In second iteration, let's say this becomes our testing or validation data. In second and third iteration, let's say this becomes our testing data, and this is become in the fourth iteration. This will giving us a A1 accuracy, this will be A2 accuracy, giving us A3 accuracy, and this will be A4 accuracy. And at the last, we will be getting the mean accuracy. Okay, so just we are importing iris dataset, cross validation score, KFold, logistic regression. We are loading our data into this. We are building a logistic regression model, and we are defining KFold. So we are writing KFold and splits equals fold. This basically the value of K, that how many folds you want to run. We are basically working here at K equals to 5. Okay, and then we are just printing cross validation score and average cross validation score. So that's how we are doing it for the KFold cross validation. So let me try and run this here. So I'll just click and run shift enter. So here the cross validation scores for different models. Basically there are 5 models. There's 1 and 0.86, 9.93, and average cross validation scores comes out to be 92% approximately. So this is for KFold cross validation 1. So now next we move to stratified KFold cross validation. So what's the difference between KFold and stratified KFold is that in case we have imbalanced data set, let's say our data is having this kind of entry, 60% of it is yes and 40% is no. Now when we try to define our folds, let's say this is our fold, one fold, what can happen that this portion of data may contain some biased data. Let's say it have 95% of yes. So now when you go for testing, it will mostly give what yes, because it's biased toward yes, since this portion is imbalanced. So to avoid this, what we try to do, we try to maintain the 60:40 ratio, or basically whatever the ratio, while splitting the data into test and train. So this is the stratified KFold. There's nothing different, but just we are trying to maintain this ratio so that our model doesn't get biased. Okay. So like for the part of the code, we are just having loading the data, we are importing stratified KFold, and logistic regression, we are building a logistic regression model, and we'll be defining k equals to 5, and next we are printing cross validation score and mean score. So let me run it. So the cross validation score is this 97% average cross validation score. Right. Next, what we are having is leaf payout cross validation. So what's the difference between leaf payout is that we have some, let's say 100 entries, then we select p equals to 2. So what we'll be doing, it will be taking 98 as training and remaining 2 as testing, and this will be happening again and again. Let's say first iteration it takes 2, and then second iteration it takes 2 more. So this will be happening up to number of times until unless it catches up whole data. So this is just p out cross validation. So let's say we take p equals to 20, because I don't want this model to be running for long. Even let's say p equals to 20 and try to run this model. It will still take too much time, I guess, because 20 and there are, I guess there are 150 entries. So first time it will be taking 20 and 130, then another time it will take another 20 and 130, and this will be happening again until we covered all 150 data points. So that is the basic intention of leaf payout. There's one more variation where p equals to 1. So this will be called leave 1 out cross validation. So in this case, let's say we have 100 entries, so 99 will be put in training and 1 will be put for testing, and this will be continued again and again, 99 1, 99 1, and so on. So this is how it's gonna work. I don't know how much time it's gonna take to run this model, but this is the basic intention behind the leave 1 out cross validation or leave p out cross validation. So let's move ahead. I don't know if it's gonna run. We'll wait and see how it works. Okay. So let me stop this. You can just try and run. It will take too much time, guys. You'll just interrupt it. Okay. Now let's look at the last, which is the time series. So it just, if we try to visualize this, what we have here, let's say this is our data initially, and this will be used for training, and this will be used for testing. Now let's say some more data point added here. So this will be used for training and this will be used for testing. Now let's another points added. What will be doing? This will be used for training and this will be used for testing. So this is how we are dividing, and this will be happen. This will take place sequentially. Right, so this is how time series classification works. So let me try and run this. Let's see what's the accuracy on this randomly generated data. So this is how we are having one point here and another point here, one point here, another point here. So this is how we are doing testing. That's it for the cross-validation technique so far. I'll be sharing this notebook with you so that you can experiment it with it. And yeah, that's it. Next we'll be looking at grid search CV and randomized search CV, and after that we'll be looking at practical implementation of that. So okay, thank you for this time.